right, so let's get started. We're going to talk about fundamentals of security. We're going to start from zero, from the starting point. And we're going to get to keys and encryption, signatures and hashes. I'm nervous closing the door. I'm nervous people might not know. Okay, whatever. Okay. So first I want to give my acknowledgments. I got a lot of material and ideas from Dr. Andy Wu from the University of North Texas, Wikipedia, of course, and this is my professor who taught the class that I enjoyed the most at university, so he got me interested in security in the first place. What are we going to talk about? We're going to talk about cryptography. We're going to define some things. We'll talk about the goals of cryptography. We'll define key terms. And then we'll talk about modern practice, how we actually implement it. Symmetric encryption, asymmetric encryption, signatures, and hashes. So just an overview. Our overall goal with cryptography is to communicate securely. We want to be able to talk to other people securely, and there are different kinds of goals within that, but basically we want to be able to talk to people securely. Traditional methods have been around for centuries, and we'll talk about the earliest cipher, one of the earliest ciphers we know about, but those are generally weak by modern standards. Modern approaches, they're at the point of integration between math and computer science and even electrical engineering. We have some hardware that plays a role also. It's theoretically possible to break all cryptography, except for one, we're going to talk about that. But the goal is to make it infeasible. You can't actually break it in practice. And it's interesting that the US classifies some schemes as export restricted munitions, like arms, like weapons. And this is like a protest shirt. What was that?
Did it still always after it was printed?
Was it still like a lot?
Is it still classified now?
Yeah.
Even after it was exported by print?
Yeah. Well, so now it's no longer restricted to be exported as printable material, but certain algorithms, because they're so strong, those are still export controlled. But yeah, they loosened it significantly. It used to be like illegal to export anything basically that's encryption schemes. In some countries like China, it is you need a license in order to encrypt things, which is a little crazy in my opinion. Anyway, so this shirt was illegal for a while because it describes RSA encryption. What are our goals? What are we trying to achieve? We said we want to communicate securely, but there's four fundamental things, and this is the most important fundamental to understand in terms of our goals. We want to provide four things. Confidentiality. That means that we want to be able to communicate in secret. We're going to define each one of these a little bit better in a minute, but we want to be able to communicate in secret so that other people can't read what we're writing. We're trying to guarantee integrity so that when we get something, let's call it a file, that we know it hasn't been tampered with. We know that what we got is what we expected to get. Non-repudiation. If you send me something, you can't claim later on, I didn't send it to you. I can prove that you sent it to me. That's an important goal. And authentication, so that I know who sent it to me. It's related to non-repudiation, but authentication is so that I know who sent it to me. And non-repudiation is to say that they cannot say, we didn't send it to you. Okay. Let's go into more detail for each one of those. Once again, these are the four main goals of cryptography. These are the things that we want to get out of it. So there's confidentiality once again. We want to send sensitive medical symptoms, let's say, to your doctor via the Maccabi website. So the question is, in terms of confidentiality, can we stop an eavesdropper from seeing your private data? Right? That's obvious. That's probably the goal that most people are most familiar with. And we know the recent iPhone case where the FBI was begging Apple to decrypt the iPhone and brought the FBI to their knees, and they needed, I don't know if you know this, they needed Israel. There's an Israeli company that helped them to and I don't think they broke the encryption. They didn't quite break the confidentiality. They found a bug in Apple's software. So the confidentiality is backdoor, exactly. Authentication. Let's talk more about that. So a bank's branch office sends to the central office of the bank a request to change the balance in somebody's account, right? So If it's a larger sum, let's say the bank wants to say to the central, Bank Benlomi, that's where I am, the branch tells the central branch, I have now an extra 100,000 shekels in my account. Now how do they know that I didn't send that? Right, that's authentication. They need to know that it came from the central bank and not from somebody else. Non-repudiation. So a customer sends their stockbroker a request to sell their stock at $10 a share. The other presentations I give are about finance, so this is a little crossover. The next day, after the stock price rises to $15 a share, I tell my broker, I didn't send that sell order. That wasn't me. That was spam or something. So now, if there's non-repudiation, the stockbroker could say, I can prove you sent that email. So that's another goal that we're trying.
What's the difference between that and authentication?
Good question. So authentication is to be able to say, I know that it was encrypted by this person. They're related. I know that this person encrypted it. Non-repudiation is after the fact, right? Not before that. After the fact, I can confirm. They're really two sides of the same coin. First is when I get the message, and the second one, by virtue of the fact that I can decrypt it, I know that this person sent it. And the second is by saying afterwards, okay, now I can confirm, I can prove in court that this decrypted message came from this person. So we'll talk in more detail, but authentication is the fact that we can decrypt it, shows that this person sent it, and for non-repudiation, a signature is showing that that person is definitely the person who sent this message that was decrypted. They're related.
You have to have integrity as well in order to have non-repudiation.
Sure. Yeah, those are also related, absolutely. And in fact, the signature provides all three of these. It provides authentication, non-repudiation, and integrity. So yeah, thank you. And we'll get to that also. The last goal of cryptography that we're trying to get out of this is integrity. So the bank's central office received instructions to transfer a lot of money from one account to another. How do they know that message, we know that it was confidential, nobody saw it in transit, we know that it was authentic from the person who sent it, we know that the central bank, the branch, did send that request. We can prove that, but how do we know that somebody in the middle didn't change the amount? And that is possible, even though we have all three of the other things, it's possible that somebody changed the amount.
And by the way,
Yeah.
part of the presentation defined the basics CIA. C is confidentiality, A is availability that you don't have,
Sure.
and the I is the integrity.
Sure.
But
Availability we're not really going to cover as like a fundamental purpose of encryption, of cryptography.
okay.
It's a little bit, it's a different focus from what we're trying to focus on.
Okay.
There's a few chairs around. Come on, man. Okay. So we're gonna talk about some key terms. Got it? Key terms? Okay. Sorry. Plain text. So these are important to understand in order to continue the discussion. Plain text. That's the text that you can read, that we can understand. That's the information, the data, before we've done any cryptography on it. Ciphertext is the encrypted information. This is after we've done what we're talking about. That's the results, that's the output. It's no longer human readable text. If it's a computer file, you can't use it as a computer file. Let's say it's a PDF. So now you won't be able to open the PDF if the PDF is encrypted, if it's ciphertext. Encryption, that's a process of converting the plain text, that's the ordinary information once again, into the ciphertext, the unintelligible text. Decryption is the reverse. That's the process of converting the plain text back, I'm sorry, I got that wrong, the ciphertext back into plain text, exactly. Cipher, that's the algorithm we're using in order to do the encryption and the decryption. Encryption and decryption are generic words. We can encrypt using all different types of ciphers. So the cipher that we specifically use, that is how we encrypt it or decrypt it. The key is that's the secret. That's what we need to guard. That's the key to doing the cryptography. If we don't have a key, then anybody can encrypt and decrypt, and there's no difference between, we don't accomplish those goals that we had before. And lastly, an algorithm is a self-contained step-by-step set of operations that a computer does. Basically, an algorithm is extremely efficient and fast way of doing something. We can do millions, billions of operations per second with an algorithm. So let's just look at this picture here. This just explains what we're doing in a big picture. We have encryption and decryption. Encryption takes the plain text, it uses the key in order to combine the key with the algorithm in order to get the ciphertext. Okay, so we have the input is the plain text and the output is the ciphertext. And decryption is just the reverse. We have ciphertext, we use the key, not necessarily the same key, maybe sometimes yes, sometimes no. We use the same algorithm, has to be the same algorithm, and we get the plain text. Any confusion about these fundamental?
Is the key doing anything, or is it just enabling the algorithm to?
Excellent question. The key is just information. Usually it's a short string. The key is a password really.
So it's just enabling the algorithm to work?
Yeah.
Just saying, go ahead.
Yeah. The algorithm is what is secure. That's what's providing the security. But the key is making it specific, the security specific to you, right? So it's your password, it's your key.
Unique.
Yeah, it makes it unique, yeah. And you know, if two people use the same key, then and use the same algorithm, you're gonna get the same, in the same file that you're encrypting, you're gonna have the same result. Okay, so let's move on. Any other questions about these very fundamental terms? I'm sorry if it's a little basic for some people who know this already. For somebody who doesn't know this is critical to diving into this.
Are you going to explain about private public?
Yeah, assuming we have time. Yeah,
I won't ask it.
No, the questions are good, but I this is not really an hour-long thing, but we're gonna see how far we can get. No, the questions are really important. So the simplest cipher is called a Schiff cipher. This was used by Julius Caesar, and it's also called a substitution cipher because very simply, you're taking each letter of the alphabet and you're substituting it with a different letter of the alphabet. Now, I don't know if anybody else did that while you were a kid. I did that also when I was a kid. You know, it was kind of cool. It's like making a secret code. But this has the algorithm is something that's logical. It's not just a random letter to a random letter. What's the algorithm? You shift it. Let's look at this codex over here. The codex has the full 26-letter English alphabet in the inside ring, and the outside ring, it also has the full 26-letter alphabet. So all you do is you just rotate the inner ring, and it lines up different letters to different letters. So you see here, A is lined up with T. B is therefore lined up with U. It's a Schiff cipher. It's not random what letters are lining up with different letters. So therefore, the key, the secret information that you have to know in order to encrypt and decrypt is how many are you shifting by, right? Once you know how many you're shifting by, you can now decrypt it and put it back into its plain text state. So once again, to encrypt, we're going to shift each letter by X letters of the alphabet, and to decrypt, we're going to move it back that same number of letters. X is the key, so therefore if X is 4, then A encodes to E, B encodes to F, and C encodes to G, and vice versa. G decodes to C, F to B, E to A. Let's look at a quick little demo. So here's the Caesar cipher demo. If we put in the plain text, we're going to say hello world. Oops, that's not how you spell hello. And we're going to encrypt it with a shift of 4. So the H we would expect to go to I, J, K, L, and so on. So it's a very simple cipher, simple to crack. Really, nobody would do that anymore. We'll talk about why on the next slide. It's called a brute force attack. The brute force attack is simply trying every single possible key. Right? Remember, the key is what makes it secure. If we try every possible key and we can scan to see whether the result, the output of putting it through the algorithm is human readable, we've just decrypted it. So if we take that, what we just looked at before on the website, and we try to shift it by 1 to decrypt it with a key of 1, it's not going to be human readable. 2, not human readable. 3, until you get to 4, it won't be human readable. And it's true with every other encryption scheme. When you get a human readable result, that means you've cracked it. And every single cipher can be brute force. It's theoretically possible. You can try that key, and and you'll see that the plain text is the result. So why do we use cryptography? Well, the challenge is, what we're trying to do is we're trying to make it, well, we'll talk about one on the next slide, but we're trying to make it infeasible to brute force it, to break the encryption. It's always possible, but we're trying to make it, except for one, there will be one cipher that's not possible, but we're gonna see if there's a way that we can make it infeasible to break it. The brute force attack could be enhanced. We now have parallel CPUs. Well, actually, that's not really true. Right now we have multi-core CPUs that are able to use parallelism, but there are fancy CPUs that are tailor-made for this kind of thing. It's really done for weather pattern. The NSA has CPUs that are very specifically geared towards brute force and other kinds of attacks. They run in parallel. They're running billions and billions of operations per second, way more than supercomputers that we're aware of. Quantum computing changes the whole picture of it. That raises the order of magnitude of how many keys we can try per second in order to brute force. You could also use advanced versions of a brute force attack, like letter frequency analysis. You could say, well, we know that in the English language, the most common letter is E, right? I said that. Let's say what Wheel of Fortune says, R-S-T-L-N-E, right? Those are the letters that they give you by default in Wheel of Fortune. Those are some of the more common English letters. So if you analyze a text, let's say you see a lot of words where it's a 3-letter word and it has the same letter as the last letter. That's probably the word the, right? The letter E is probably at the end, and that's a move. My point is that you can do frequency analysis. You can analyze the ciphertext to try to make your brute forcing more intelligent. Another example of that is a dictionary attack. Most people's keys are going to be words. So a dictionary attack is still a form of a brute force attack. You're still trying to brute force Yishkisod.
Yishkisod.
You can brute force. It's still considered a brute force attack because you're trying different things that you don't know. You have no idea, but you're limiting the set of what you're trying to something that's more intelligent to try, and you're probably going to have more success. So that's a brute force attack. What's the solution? The solution is to make the key random. So if the key is random, now it's harder to run a brute force attack against it. A dictionary attack won't work, right? That's why when you try to log onto a website, it tries to get you to use random characters and things like that because it makes it more random. It makes it harder to limit the key space, the possible keys in the brute force attack. You also want a large enough key so that there are, once again, too many possibilities to guess. The number of possibilities is the number of possible values in each character of the key. This is a little math. To the power of the length of the key. And we'll see that once later. You don't have to know this. This is just for people who are interested in the math of it. But the key space, the number of possible keys, is the number of possibilities that each character in the key can be. So let's say it's an alphanumeric password, so 26 letters, 10 numbers. So it's 36 possibilities to the power of however many letters are in the alphanumeric characters are in the key. It's a little mathematical. No need to really understand that. Good encryption schemes have so many possible keys that it's effectively impossible to brute force it. There are a few other mitigations you could do against brute force attacks. For instance, the Windows login screen. If you fail a login, it'll delay a certain amount of time, a few seconds, before you can try again. If you're trying to do billions of, if your brute force attack relies on being able to do billions of attacks per second, and it gives you a delay of like 3 or 4 seconds every time, it's not going to work, the brute force attack. Before you do those billions of attempts, it's going to be trillions of years. And another mitigation is to allow the user to configure a limit to how many times you could guess wrong before it just wipes the data. And Dropbox has this, BitLocker has this, a lot of things where you have secure data on it. They allow you to say, if they guess the wrong password 10 times, just delete everything on the device because it's so important to me that they can't get this data that I'd rather lose the data than let them try a trillion times. Here's an alternative to cryptography, very interesting. It's called steganography. It's about hiding information within a file, a message, an image, or a video. It's in plain sight. It's right under your nose, but it's hidden. you try to conceal the fact that a secret even exists in the message. So this way nobody even knows that there's a secret and you avoid scrutiny. If you have an algorithm, if you have ciphertext, and you put it out there, let's say somebody downloads some code of ours, some RSA code or EMC code, it might be encrypted, and now they know they have a goal. Now the hackers have a goal and they're going to try to find a weakness and try to hack it. But with steganography, the goal is for nobody to even know there's a secret there. So the simple example is the child's invisible ink. So it's there, it's written, but you don't know it's there until you do whatever you need to do to show the invisible ink. So this is the most common type of steganography, and this was used by Al-Qaeda back in around the year 2001. Very popular way for them to communicate on the internet. They might start with just a regular image file and share that, and want to share that image on a message board online. And before they would share it, they would just adjust the color every, let's say, 100th pixel, and adjust it to a shift. Let's say you can even use like a shift cipher, right? That would encode the information in there, and then all the other person has to know is find every 100th pixel, and then remove this shift, and now you have the secret data that I wanted to communicate with you. It's a change so subtle that nobody would realize that it's there without specifically looking for it. It basically is impossible. The only way to break this is to have the original picture and then compare it with the changed picture. Then you can see, hey, every 100th pixel has been changed. This is steganography, let's try to break it. This is very interesting. Modern laser printers, not all of them, but really nearly all of them, as far as I understand at least, they use anti-fraud dots. Basically, when color laser printers came out, the US government was nervous that people would start printing money. So they said every laser printer has to, and this is to scale, this is 1 centimeter, has to have a series of dots that identifies the serial number of the printer that printed it. And this way they can prove who printed this, and obviously a database of which printers were sold to whom. But those are privacy issues, there's just a whole different discussion. But steganography, this is an alternative to cryptography, really, really fascinating field. I wish we had more time to go into it. Let's look at an example of steganography from everybody's favorite show, if it plays.
It's 2 in the morning.
I couldn't sleep because I thought there might be a sign of my mom in one of these articles. They never did find her body.
Then what was in the coffin?
Last week's garbage, and it's the big update. But it doesn't matter because my mom is alive, see? I-am-okay. Get it? I am okay.
Okay, homie. If it makes you feel better, I think your mom's all right, too.
Hey, as long as we're thinking about her, Grandma's still alive.
Come on, big guy. This'll help you get to sleep.
Homer, your mother loves you. I escaped from the bus the moment before it plunged off the cliff. I then hitched a ride from a nice young couple. We had lunch at a lovely diner. They had clam chowder, Rhode Island style. I never knew there was such a thing. And the crackers kept on coming.
So as long as you can hide information in plain sight without the person realizing, that's steganography. So let's talk about the key. The key is the only secret, not the algorithm. In fact, it might sound a little counterintuitive, but this is a quote from the US Nuclear Guide. The security of a system should depend on its key, not on its design remaining obscure. So there's a quote misattributed, but security through obscurity is not security. Obscurity meaning hidden. So if your security relies on people not knowing the algorithm that you're using or anything other than the key, you don't really have security. And counterintuitively, we say that making the algorithm public can improve the strength of the algorithm, because the sooner the public finds holes, the sooner they can be addressed. That's why people in the security community are very uncomfortable with algorithms that are advocated by the NSA, because presumably they have a backdoor. We'd like everything to be public. We'd like to be able to have the public always identifying weaknesses so that we can prove them. what are the parameters of the key? What makes a key? Well, we have the, first the ASCII secret. We also have the length, the size of the key. And like we said before, that makes a big difference in how hard it is to brute force. So we usually talk about the length or the size of the key in terms of number of bits. So when you hear 128-bit encryption, that's this, the length of the key. The longer the key, the harder it is to brute force or to otherwise compromise. The key space is the term that we give to the length of the number of possible keys, or all possible keys. So if we look at a very simple example, this is binary, so you only have zeros and ones, and that's, since we do all this with computers, effectively all keys are binary. So the key length here, this is a 2-bit key, and you really have a key space of 4 possibilities, right? It's a 2-bit key, there are 2 possibilities. In binary, you could only have 2 possibilities per possibility. So once again, this space could either be a 0 or a 1, and this could be either a 0 or 1. Well, here we see enumerated the 4 different possibilities. This is a 0, 1 here, and this is a 0, 1 here, so you have 0 and then 1, 1 and then 0, 1 and then 1. This is the entire key space of a 2-bit key. Do not use a 2-bit key in your encryption. Let's talk about exclusive OR. You don't have to understand this. This is a little mathematical also. This is not so crucial. But just know that this is how encryption is generally done, at least with symmetric algorithms. This is the most common way of applying a key to plain text in order to get ciphertext. So what does that mean to apply a key to plain text? Apply means do an exclusive OR operation. That means you take the plain text. For every bit of the plain text, you do an exclusive OR. So let's say the first key of the plain text is a 0. You do an exclusive OR with the key, with the first bit of the key. So the key is Y. So 0 XOR 0 gives you 0. That's because exclusive OR says, I only want a 1 if the 2 values are different. You don't have to understand any of this except for the fact that we use exclusive OR in order to apply a key to the plain text, and that gives us our ciphertext. Roughly speaking, I'm simplifying things here. Why do we use XOR, exclusive OR? Well, it gives us 2 really important properties. If A XOR B is C, then we're guaranteed that C exclusive OR B gives you A. That should sound like decryption, right? If we can encrypt it, then we could decrypt it using the same key. So that's why it's so important, at least in symmetric encryption, which we'll talk about in a minute. If we're able to encrypt it, we can also decrypt it using that key. That's why you use XOR. Reason number 2 is because we want the ciphertext to have no hint of the plain text. So if you use a different operation, let's say an AND operation. An AND is more likely, to people who know computer science, an AND operation is more likely to yield a 0 than a 1. So the image, the output, the ciphertext, is going to have a strong remnant of the plain text. Basically, it's not such an important concept, so we're going to move on, but the point is that you have a 50% chance after applying the key to the plain text, you have a 50% chance of having 1 or 0 in the ciphertext. It makes the ciphertext completely unintelligible. Here's some visual examples. Here you see on the right from Wikipedia, they show a Venn diagram of A exclusive OR B. So this is A, this is B, exclusive OR. When they're both red, the result is 0. But when one is red, then it's 1. This is A, B, and C. Not so important. If you're interested in the math, you could take a look here. To encrypt, you have the plain text, and then you XOR it with the secret key. So 0 exclusive OR 1 gives you 1, like we said, and if you follow it through, you'll see that it all works out. And when you decrypt, you just take the ciphertext, and you need the secret key, and when you XOR them together, you just get the plain text back. Really cool property of XOR. That's what makes it so useful in encryption and decryption. Let's talk about the strongest cipher that exists, and I'm speaking in a theoretical sense too. The strongest cipher is called the one-time pad. Very simple concept. It's basically the key, you have plain text and you have a key just like any other cipher. The key is the same length as the plain text. So I want to encrypt some secret message. I want to encrypt some secret message. So what I need is a key that's at least as long as that plain text. Here's the problem with that though, how am I gonna get that key? If I, in order, when I get that key, now it's exposed to the, you know, it's susceptible to being hacked, to being eavesdropped. And if somebody eavesdrops on the key and they have the key, they can break it. So how do I securely communicate the key, which I'm using to securely encrypt the site, the plain text? How do I securely communicate that? It's like a chicken and egg problem, right? So there is,